Okay, thank you so much and welcome back to our next video. So in this video, we will begin to focus with we'll begin to focus with the graph, the same thing, and that will we will proceed with the next topic, which is all about the spanning tree. So what is spanning tree when you think all about the spanning tree? So when we say spanning tree, that is talking to a subset of an undirected graph that contains all the vertices of the graph connected with a minimum number of edges in the graph. So meaning does not have any cycle and any vertex can be reached from any other vertices. The applications for this, we can apply that in your network design, routing algorithm, cluster analysis, and more. There's a lot of usage. I mean, the spanning tree is really useful in some certain cases. Now, when we say spanning tree, that is talking to any kind of subgraph that consists, for example, in this particular graph, you have four vertex. And if for your four vertex, when you will create a spanning tree, it should be n minus 1 edges. So how many vertex that you do have? Your n vertex, it will be n minus 1 for representing the edge. So, and it does not perform any cycle. So that means to say suppose in this kind of spanning tree, or spanning tree for that one, pwede siya, it could be A, then B, and C, and connected to D. So that is the example of spanning tree that really consists of all of those particular nodes, and your edges is really n minus 1. That's how it works when we are talking to spanning tree. Now, has n minus 1 edges, what I mentioned, where n is the number of nodes, and connected graph. So it must be a connected graph. It's not disconnected. And you cannot perform a spanning tree if there is a disconnected graph. Can have more than one spanning tree. Of course, in this particular graph, either you can have, for example, you will just remove B and D, or this edge BA and AD in order for you to have subgraph, or this one AD or BD in order for you to perform another subgraph. That's how it works. Is minimally connected. So removing one edge from the tree will make the graph disconnected. So say, for example, if you remove this three edges, it will be disconnected. So be mindful with regards to that one. A tree that connects all vertices of an undirected graph and not applicable to directed graph. Because of course, class, in your directed graph, it is actually really hard to produce a spanning tree when it comes to there is a direction. So that's why it's only applicable um for the undirected graph. So the type usually of spanning tree, we do have the minimum spanning tree as well as the maximum spanning tree. When we say minimum spanning tree, we can also go ahead and check that later on. But spanning tree example for this particular given, the first spanning tree that we have here is something like that. It could be like that you do have A to B, B to D, and A to C, A to C, and A to D, and A to B. That's fine. And we also do have another here. So third and fourth and fifth and sixth. So of course, class, in your spanning tree, how many vertices that you do have here? How many edges that you do have currently? 3, 4, 5. And you actually created is 6 spanning tree in that certain vertex. So it's actually a lot of spanning tree that they can perform. As what you can see right here that um there's a lot of possibilities that you can do with. So let's move on with the minimum spanning tree then. When we say minimum spanning tree, that is can be defined as the spanning tree in which the sum of the weights of the edge is minimum. So that means to say, minimum ang numbers. Weighted graph siya nga, that is talking to weighted undirected graph where we are adding all of those minimum edge. So in real world situation, we can apply that. This weight can be measured as the distance, congestion, traffic load, or any arbitrary value, which is denoted to the edges. So by the way, in that certain minimum spanning tree, there's a lot of applications that you can also use then. That is really useful in such manner. And of course, in this particular minimum spanning tree, the minimum for that one will be the 4, will be the 7, because 1 is a cycle, so we cannot choose 1. And 8 could be, so 4, 8 plus 7, we can do that one. 4, 8, 7, and that is equals to 19. So that is your minimum spanning tree in this particular graph, because you cannot choose 10 since it will perform a cycle, and that is greater than 2 um your other values right here. But this is not following any principles or types of spanning tree methods yet, because we can apply minimum spanning tree when it comes to the Prim's algorithm and Kruskal's algorithm. Now let's actually move on to the maximum spanning tree. When we say maximum spanning tree, it will be different by this minimum spanning tree. I'm so sorry that I was able to put that still there as minimum spanning tree. So that should be a maximum spanning tree. So when we say maximum spanning tree, that is talking similar to minimum spanning tree, but instead maximizes the total weight of the tree instead of minimizing it. So common application where you want to maximize connectivity in a weighted graph. So our focus in that particular right now, this will be, you will choose the maximum, it will be 10, could be 23, and it could be 8. So that's how you will do that. 10, 8, and 23, you add that all, and that will be the maximum spanning tree of that specific graph. So that is actually the example of maximum and minimum spanning tree as right now, but that is not using the Kruskal's and Prim's algorithm yet. So in the next video, I will be going to explain how to work on with the Kruskal's algorithm and the Prim's algorithm. So see you there.